I'm Igor Jovanovic. I would like to tell a little bit about how one can use light to make measurements of materials that are relevant to verification, nuclear materials, but also materials that are not radioactive necessarily. So, so this is the work that has evolved over the years. We have been funded not only by the Consortium for Verification Technology, but I'd like to take opportunity also to thank the other agencies that supported this work, especially the Department of Homeland Security. So first, I'd like to introduce the team that has been working on this, and three of our students are actually here, Kyle Hartig, Phyllis Morgan, and Taylor Duffin. In fact, two of them are finishing very soon, so for those who are interested in hiring, this is a good opportunity to talk with them. Phyllis is finishing this semester, and then Kyle probably next semester, and Taylor is our new student, so he's here as well. We also have a postdoc, Isaac Igor, and he's been working with us for a bit less than a year. So when we met about a year ago, I tried to formulate, why we would like to do this type of measurements with optical techniques. What are some of the features, some of the advantages of these techniques that perhaps lead to special capabilities in these measurements? So, so I'd like to go through, just briefly go through those, and maybe take some comments at the end. This is always open for discussion. But one thing that always strikes me when I consider these techniques is that one can make really nice in-situ measurements without preparing the samples, which is something that is been very time-consuming in many applications. The other aspect of this is that this is essentially an active interrogation measurement, but one that produces zero dose, right? Zero radiation dose. So one can perform essentially active interrogation while imparting a zero radiation dose. Next thing is, if you work with the systems, then you realize that the limits of these measurements have been pushed to the physics limit. Now they're no longer engineering limited; they're limited by the physics, and this is even possible using commercial off-the-shelf components, in the laboratory. So, very exciting thing that I like to tell students when they start playing with this is that you can really push the physics all the way to the limits with this already. You can go to very high spatial temporal resolution. Again, they're already physics limited. Spectroscopy, you do a lot of spectroscopy measurements with this, and interesting aspect of this is that you're typically not limited by the statistics of information carriers. When you make these spectroscopic measurements, you try to push your resolution higher. Finally, it's possible to reject background very well because it's an active interrogation technique. There are a lot of characteristics of the signal that distinguish it from the background. And you can detect non-radioactive materials, something that many techniques cannot do. So there are, of course, drawbacks like with any other technique, and one is that you need direct line of sight to the material that you're trying to investigate. Second is that you're limited to characterization of bare surfaces, so you cannot characterize something that is shielded. And then finally, you're susceptible to complexity that arises in production of plasma, which is inevitable. So there are effects called matrix effects, the interferences in the spectrum that you have to understand and try to deconvolve. So technique that we have been focusing on, this is not the only one that we are looking at, but the one that we have spent most of the time working with is the laser-induced breakdown spectroscopy. And this is a technique that has been used, for decades. It's in fact used in very hostile environments. It's used on Mars, so it makes the news still today. The idea here is to use a laser to produce a microplasma on the surface, and then to use the optical emission, from that plasma and characterize it spectroscopically. So to collect the light, send it into a spectrometer of some type. There are different types of spectrometers one can use, and then analyze that spectrum and then try to draw conclusions about the characteristic of the material that is being measured. And in order to do this, there are commercial systems. There are also the ones that are more research-based. We have constructed a very general purpose system in our laboratory. This is what's shown here on the right side. So we have a very nice vacuum-based system, the one that we can essentially investigate various characteristics of the optical in various conditions, including different pressures, different ambient gases, etc. So very general purpose, but I don't want to give you a wrong idea that this is the ultimate size of what's possible, because there are already backpack-based systems that have been built, places like Los Alamos that have been deployed. So this is a general purpose system. I mentioned in-situ analysis. So originally we started working on this in the context of nuclear forensics, where it struck us that this is really exciting because one does not need to rely on time-consuming collection, preparation of samples, sending those samples to analytical laboratories, and then making this time-consuming analysis, a process that normally takes a very long time. In contrast, with techniques such as LIBS, but also some other optical techniques, the analysis is rapid. There's no sample preparation. It's also possible to make measurements at a distance. It is not, very straightforward, but it's certainly possible. That's something that we are working on. The drawback of these techniques is generally that the sensitivity level that can be achieved is lower than that possible in techniques that involve this complex sample preparation. But there are certainly advantages that need to be considered in the context of verification, where where the speed of this analysis and the speed of arriving with a conclusion after the analysis could be extremely important. So there are three main topics that we have been studying on the CVT. So one of them is the isotopic measurements of uranium. So this has been a very exciting year for us. We have really good results. I'm going to show you, and I think some of you may have already seen it. So Phyllis presented a poster, and it's still hanging there. So for those of you who are interested, it's a poster 12. And then the second topic we are working on is the measurement at a standoff. So how do we make these measurements at considerable distances? So not necessarily only in accessible facilities, but maybe even the ones that are inaccessible. And then the matrix effects, which is this problem, trying to address the problem that the samples are not really pure, that the materials that one tries to analyze don't consist of a single element, but rather of there's usually some complex composition involved, and how does one make quantitative conclusions about the composition in such conditions? Turns out to be quite complex. So there's a poster by Kyle Hartig that has also been addressing those topics. So to start with the isotopic measurements of uranium, I mentioned this has been a really good year. When we were here last year, we said that maybe this time we could possibly arrive at this point that we'll actually make the isotopic measurements using a very compact instrument in our laboratory. Normally this is pretty challenging because the isotopic shift is very small, atomic isotopic shift is very small, very large devices and complex devices are needed in order to resolve it. So this is not just a physics problem of trying to separate these lines, but it's also an instrumentation problem. So we had a collaboration now for a couple of years with Jill Scott at Idaho National Laboratory, and so Phyllis has spearheaded that collaboration a couple of years ago. And the idea behind this collaboration was, can we build a really small, compact instrument that we can possibly put in a backpack in the future? And the idea here was to combine two principal techniques that are possible to be used for optical spectroscopic measurements. One is a standard method that uses dispersive spectroscopy, so using a grating or prism or such optical element that essentially maps angularly the frequencies onto a detector plane. That method is normally used in spectrometers, but it's very limited by resolution. The other method, which is much more promising when it comes to resolution, is interferometric method. So relying essentially on the differences in transit time, or rather in the optical phase, of different frequencies of light, and relying on constructed interference of these frequencies in order to achieve very high spectral resolution at the expense of a lot of degeneracy in the measurement. And especially this is the problem with uranium, which exhibits very complex spectrum. So we decided to combine those two methods in what we call a hybrid interferometric dispersive spectrometer concept. In fact, Phyllis has a really nice acronym for this in her dissertation. We call it Defender, and I even forgot what each letter stands for. But so the idea is in horizontal axis here we can get a crude resolution measurement. This is what you normally get. But in this vertical axis, orthogonal to the dispersive measurement, we have interferometric measurement. And this is all done on the same detector, and it's done in a very compact footprint. So we can reveal the fine structure of the spectrum in this vertical axis, and you can see already here splitting of the spectral lines that we see, and crude resolution on the horizontal axis. So we actually proceeded to build this, and we validated that, and in the UITI meeting, which was only a couple of months ago, we have shown how we have validated some preliminary work on how we have validated these measurements using mercury lamp. There's certain high-resolution features in those spectra that were used in order to validate it, and we found that indeed that worked. And so we in fact developed a full reconstruction method for these measurements that were done using this method that was published recently, and we have validated those. That reconstruction also with a standard measurement method with a very complex instrument, very expensive instrument that is used at Los Alamos called Demon. So you can see very good agreement between our method and that method that is used at Los Alamos. So the big challenge here was, can we do this with uranium? And this is not only a measurement challenge, it's also a little bit of a regulatory challenge. So over the years, we have worked, closely preparing, to be able to do this with the Nuclear Regulatory Commission, as well as with our Radiation Safety Office, that finally helped us to authorize this measurement. So we've been able to borrow two foils. One is natural uranium foil with enrichment of 0.7%, and the other one is the HEU foil with reported enrichment of 93%. Which we were able to actually use in our university setup in this way, in which we perform this ablation in a sealed environment, and then use the specific procedure in order to avoid any kind of contamination at the laboratory, which, by the way, we never saw. So the amount of material that is removed is minuscule indeed. And we did validate, these. The fact that these samples really do have this kind of composition using standard gamma spectroscopy. I'm not going to get into that in detail, but this is the main result. So we measured the interference pattern that arises, between when measuring both natural uranium samples and highly enriched uranium, and we found, and this is even visible by eye. We have isotopic shift that we see with highly enriched uranium. It's different spectrum that we see than we see with natural uranium, and this is sort of the crude, the projection essentially of that measurement on one dimension on the angle which is the principal axis of the analysis in this measurement. So we see two characteristic lines, and we see characteristic isotopic shifts associated with these. And when we reconstruct them, we find exactly the two isotopic shifts that have been previously measured for uranium-235 and uranium-238 using very large complex instrument. Now we can do this in a very compact form. So one is a 25 picometer shift, and the other one is a 6 picometer shift. Both of those are on 424 nanometers, so this has been now submitted for publication. So this is our principal result here, and notice that we have not really measured enrichment yet. We have discriminated between highly enriched uranium and natural uranium. So in the future, we hope to have access to samples with a wider range of enrichments, and this is a little bit of a simulation of what we expect to see in our measurement that would allow us to essentially measure isotopic composition very quickly using this method. So moving to the next topic, I don't have a lot of time, but I promise I'm getting closer to the end. Measurement at a distance. This is very interesting. I just wanted to mention filamentation is a way to deliver pulses over very long distances. So we're still relatively early in deploying this for our measurements, but we are making progress. It's interesting that this was discovered about 20 years ago here at the University of Michigan, this method for delivering pulses over very long distances. it's known that one can measure composition over a very long distance. So we are moving forward with developing our experimental capabilities to make this measurement. So we extended our test chamber to accommodate filamentation tests in nuclear materials of our laboratory. So we hope that soon we will also have some preliminary results in how these measurements can proceed. There's more detail on how we characterize the propagation of these pulses. It's essential to our understanding to know what the excitation on the material surface is going to look like. So we're making multiple measurements to learn about the properties of these filaments. Some preliminary measurements. We're moving to femtosecond LIBS of uranium, and we have learned certain limitations of how we can make these measurements more robust. One of the things we learned was the plasma is rapidly expanding in those conditions, so we're going to have to operate in slightly different conditions in order for these measurements to be successful. And finally, the final topic that I mentioned is trying to move to quantitative analysis in these conditions in which samples are not pure. So they do have a fairly complex composition usually. They will consist of multiple elements. And the plasma that results from interaction with the laser exhibits fairly complex spatial-temporal resolution. A lot of plasma photodynamic interactions take place, and how to deconvolve these measurements into some kind of quantitative interpretation has been very challenging in the past. So we've been collaborating with Los Alamos, with James Bearfield, and others in order to try to employ some of the advanced modeling tools that Los Alamos has developed in order to try to deconvolve these measurements. We did have a recent success in a relatively simple system with copper, but we hope that we can advance this fundamental understanding to more and more complex systems, such as the ones that are relevant to the verification. So with that, a list of our publications and presentations since last time, and I would like to, we have a long list of acknowledgements. This has been supported by others, not just by the Consortium for Verification Technology, especially a number of fellowships to students. And with that, I'll take any questions if I have time. Thank you.
If we then integrate the number of counts within a time window, which in this case was about 200 nanoseconds, we can also